Hi everyone, in today's video I will be explaining how to maximize the range and endurance of an aircraft, that is, in its cruise flight phase. Now let's get started. First, in our cruise flight phase, we're going to have to consider the four main components: the thrust, lift, weight, and drag, these four forces that are acting on your aircraft. And now in your cruise flight phase, you're going to have to consider the fact that the weight is equal to the lift and the thrust is equal to the drag. So the forces are balanced. Now let's start off with maximizing our range. So first of all, when we're considering range, we have to consider a parameter, and that parameter is a specific range. And our specific range is going to be equal to the velocity of our aircraft, or the airspeed, divided by F dot. And F dot is not the force, it is simply the fuel consumption rate. It's fuel flow rate. Your F dot is going to be how many kilograms of fuels is being flown per second. So kilograms per second, and your velocity is simply meters per second. So if you just go ahead, meters per second divided by kilograms per second, you're going to get that your units for this is meters per kilogram. And what this says is that how many meters is my aircraft going to travel per kilogram of fuel. We're going to have to maximize this in the sense that we're going to want to travel a lot more distance per kilogram of fuel. And so maximizing specific range. Okay, so another way to express our F dot, fuel flow rate, is by considering the fact that the fuel flow rate is simply your shaft power, which is denoted as PBR, multiplied by the specific fuel consumption. So your shaft power is simply the output power generated by the shaft in your engine, in the aircraft's engine. Okay, now we know that we can substitute this F dot right over here with here. Just gonna write SR in short for specific range. It's gonna be V over PBR times CP. Now let's go ahead and take one more step. And in this step, what we're essentially going to do is try to rewrite another expression for our shaft power. And this is simply coming from our efficiency formula, which states that your propulsion efficiency is equal to your power available divided by your shaft power. And our propulsive efficiency is simply the measure of how efficient is our engine in mechanically propelling the aircraft. So this is the available power that we physically sense in the aircraft as it moves, which is power available, and this is the power that is generated by the engine. But not all of this shaft power is converted into mechanical work that can perform the propelling of the aircraft. Hence, we have this measurement. Now what we can do is we can take PBR here and say that PBR is equal to PA over eta P. And so if we go specific range, it becomes V over power available divided by your propulsive efficiency times CP. Now I can go one more step further and evaluate the value for power available. So from physics, we know that power is simply force multiplied by velocity. And our force, which pushes our aircraft forward, is the thrust force. But as we discussed earlier, since we're dealing with cruise flight phase, our thrust will be equal to the drag. So the forces balance out. So we can also say that our power available is simply drag multiplied by velocity, instead of saying thrust multiplied by velocity, because they're the same thing since we're in cruise flight phase. So it's going to be V over dV times Cp right over here over our propulsive efficiency. Just simple algebraic manipulation. Now we see that the velocities here cancel out, and our specific range is left with propulsive efficiency divided by drag times specific fuel consumption. Okay, great. Now this was the difficult part, I would say, to come up with this equation. Now what do? We see that our propulsive efficiency and our specific fuel consumption is something that are constants. So we can say that our specific range is dependent on our drag force. And now what do? To maximize our specific range, we can minimize the drag force over here so that our fraction yields to a large value. And so let's go ahead and minimize the drag force here. Okay, so here is our aim. We have to minimize our drag force. And here's what I like to do. So I would say that your drag force is simply, you can rewrite it as drag multiplied by lift over lift. And lift, this is force. And so this is 1, so it's not going to change anything. And so this expression mathematically holds true. But here's where the magic comes into. So if we go ahead and write this, we're going to get d over L. d over L times L. So what is d over L? d over L, well, the drag force equation says that it is rho s, and the lift equation states that 1 over 2 lift coefficient v squared rho s. Rho is the density and s is the surface area. Now, here we have times L. These cancel out, and we're left with CD over CL. Drag is equal to CD over CL times lift. Okay, but we also know that our lift force is also equal to our weight force, since we're again in cruise flight phase. And so we can rewrite this as CD over CL times weight. And now we see something very interesting, because our weight is technically constant, and we're going to only have to deal with CD over CL in order to minimize our drag force, because these are going to change, because these themselves are also dependent on velocities, which we're going to see further on. So right now our aim is to essentially minimize CD over CL, right? Because we said that weight is constant. And so now our aim is to minimize CD over CL. So, okay, if we expand CD, we get something like this. We get CD 0 plus K1 CL plus K2 CL squared. And CL, we're going to write it down in the denominator like so. So our drag coefficient is simply made up of lift coefficients and constants, as we see K1 and K2 here, and as well as CD0. And for those who don't know what CD0 here is, CD0 stands for zero lift drag. And these are all components that are related to the aircraft itself. Basically, they are characteristics of an aircraft, and it differs for each aircraft. So it was beneficial to bring our expression to right over here, because the manufacturer of the aircraft automatically knows it's K1, K2, and CD0. Anyways, now we have to minimize this, right? Well, how will we do it? We see that this CD over CL right over here is a function that is dependent on CL, which is the lift coefficient. And so what we can do here is that we can take the derivative of this expression with regards to CL and equate it to 0. And hence we're going to get the value of CL where our CD over CL will be minimized. Now, to begin to find the derivative of this function, I'm going to divide every term by CL to simplify my expression. And now what I'm going to do here is that I'm going to take the derivative of this function, d over dCL, derivative with respect to CL. And now when we find the derivative of this, it's going to be minus CD0 over CL square. And since k is a constant, this derivative is 0. And it's going to be plus k2, the derivative of this. And then we're going to set the derivative all to 0 in order to find the minimum. K2 is equal to CD0 CL squared, and our lift coefficient is going to be square root CD0 over K2. And so if you're wondering why is there only one solution, well, CL has to be positive, it can't be negative, and this suggests that square root of CD0 over K2 is the optimal value for our lift coefficient such that our drag is minimized and hence our specific range is maximized. Now what is this really useful for? Well, check this out. So now that we know that our optimal lift coefficient is square root of CD0 over K2 such that our specific range is maximized, we can find the velocity such that the pilot should be flying at in order to maximize its range, right? So I know that my velocity formula is going to be something like this. Well, it's lift is equal to 1 over 2 v square s, right? And now we said that in cruise flight phase, our lift is also equal to the weight. And so if we go ahead and find an expression for v here, rho s, and square root that all. And now if you come ahead and plug this value of CL right over to this velocity equation, you're going to be able to find the velocity that the pilot will need to fly in order to maximize its range. And we know these values, CD0 and K2, because when manufacturing the airplane, you will be given these values. So let me go ahead and write this down. CDs, all that, and this is the speed that I will need to fly in order to maximize my range, in order to go a maximal distance per kilogram of fuel. And this is really important if you're only starting to learn aerospace engineering. These are some of the most fundamental concepts that you'll need to know and apply in your further studies. Now we're going to discuss endurance. Endurance is simply how long can an aircraft fly with a given amount of fuel. So I want to maximize endurance for many things. First of all, if we're having projects where we're trying to stay up long in the air, endurance has to just generally has to deal with time. So if we want to stay up long in the air with a given amount of fuel, we'll have to maximize this parameter. And so endurance is simply related to your fuel flow rate, which we discussed earlier, the kilogram of fuel flown per second. So kilogram of fuel per second. We would want to minimize this parameter right over here, fuel flow rate, in order to maximize our endurance. I'll label endurance as E, and endurance is proportional to 1 over F. So think of it like this. The lower your fuel flow rate is, the higher your endurance is. So minimize F dot. As we discussed earlier, our fuel flow rate is simply Cp times shaft power. And then we can say that our propulsive efficiency was power available divided by our shaft power. But this time, instead of power available, we're going to use power required, P sub R. And this is because the power required and power available, they're both same things when we are in our cruise flight phase. And so effectively our F dot becomes Cp times PR divided by our propulsive efficiency. And now, since Cp and our propulsive efficiencies are constants, we would have to minimize our power required in order to minimize our fuel flow rate and hence maximize our endurance. So for those who don't know, power required is simply your drag multiplied by your velocity. Essentially, what power required is the amount of power that you would need, that an aircraft would need to overcome drag and move forward. So we discussed earlier that we can express d as d times L over L, since it's the same thing, times v. Mathematically, it's the same thing. And what this leads to is CD over CL times L times V. And your L right over here in cruise flight phase is going to be the same as your weight. And so we can rewrite this CD over CL times weight And now look what we can write here instead of v. Instead of v, we can write here all square rooted. So instead of this, we can write this. Square root 2 times weight over rho SCL. And now, this is our power required. Let's go ahead and do some mathematical operation on this L cubed. Now think of it like this. Since our aim was to minimize the power required, and since these terms right over here, the weight, the surface area, and the density, and since they are constants, we'd have to be dealing with CD squared over CL cubed, because these are the variables. And to minimize our power required, we would have to minimize CD squared over CL cubed. So this is one way. The other way, however, is to maximize the reciprocal of this, because if you go ahead and say if you maximize CL cubed over CD squared, you're going to get the same as minimizing CD squared over CL cubed. This is simply a mathematical principle. So if we go ahead to minimize PR, we are going to want to maximize CL cubed over CD squared. Well, I would want to take the derivative of this expression right over here, and essentially I'd like to equate it to 0 in order to find the maximum value of CL, because we know that CD is actually composed of CL. DCL. Now, what would I use? I'll use the quotient rule over here. So first take the derivative of the numerator, 3CL squared times CD squared minus CL cubed times 2CD. Now we'd also want to use the chain rule since CD is composed of CL, and we're gonna say, I'm just gonna write it over here, DCD or DCL right over here. Just know that it's supposed to be times this right over here. This is all over CD to the power of 4. And what we do, we equate this derivative into 0. Now, mathematically, you'd be like, okay, I have the CD to the power of 4 here. What do I do with it? Well, you know that CD can never be equal to 0. And hence, you can move it to the right side, cancel it off, and leave yourself with a very solid equation to 0. If I move this to the right side, if I do some canceling out, I get 3CD is equal to, this cancels out with this, and DC D over DCL. Now, we get this expression. What do we do with it? We have this DCD over DCL. As we said, CD is simply CD0 plus K1CL plus K2CL squared. And then if we find the derivative of this with respect to CL, we get something like so. So 3CD equals, you can expand this yourself, but eventually you're going to get something like this. So DCD over DCL is going to be K1, then it's going to be 2K2CL. Then we take CD and we expand this as well, because we know that it's composed of CL, right? So we get 3CD0 CL squared. And this is equal to DL. Now, if you algebraically expand this and combine the like terms, you're going to get something like this. Minus K2CL squared plus K1CL and plus 3CD0. And this is going to equal to 0. And from here, what you want to do is you will simply need to solve for CL squared. This is a quadratic equation. So from here, I can say that my solution for CL, there's going to be two solutions, right? 1, 2. It's going to be equal to minus B, which is minus K1 plus minus square root of B squared K1 squared minus plus, actually, makes it 12 CD0. And this is over 2A, which is minus 2k2. Okay, and this is our solutions for CL, where our endurance will be maximized. And as well, we can go back to the velocity equation, where we said the velocity was equal to the square root of 2 times the weight, CL rho S. And you can find the solution from here. You can plug it in to the CL right over here, and you're going to get the optimal speed that you will need to fly in order to maximize your endurance. But there are two things that you need to consider when finding the solution. So number one is that your solution cannot be negative, because CL cannot be negative. And as well as your solution cannot be greater than your CL max. And this is the maximum value of your lift coefficient which your aircraft can handle in a specific condition. And so with that, guys, we wrapped up with personally my first aerospace engineering video. And I hope this was intuitive, and I hope this was useful for you guys, because many of you guys will need to learn these and will need to apply this in your first year aerospace engineering and as well as in your future projects. I hope you enjoy this. If you have any comments, suggestions, thoughts, leave it in the comments down below. Like the video, subscribe, share if you think it's valuable for your other friends who study aerospace engineering or who are thinking to study aerospace engineering. And so, yeah, that's it. Thank you guys. Bye bye.